So this was the problem that we were in the middle of last time, and we'll start right there. All right. So this is the problem we're going to start with that we talked about before we started last time, but we'll finish it up today. Also, during the last class, I said something about an assessment quiz for the purposes of some kind of evaluation. That's going to happen today. So after class, I'm going to post that onto Canvas. Finish it by midnight tonight. It'll be one optimization problem, so it won't be really long. It's one problem that should be manageable. It won't take a ton of time. But it will be formatted differently than the other exams that we've had. So make sure to carefully read the instructions that are there about how you actually submit it to be great. So what we did last time, and to be honest, the material that we covered last time is a tough day for me, as well as I imagine a lot of you, because it's a lot of kind of notation and somewhat abstract. And even the takeaway is a little lackluster, because it's saying that this idea we have that when you draw some function, there's some shape below it. That shape should have an area to it. What we did was justify and say, yes, there is some number, which we can call the area, and this is the way that you come up with that number. And what those areas look like are these limits of Riemann sums. So without the limit part, this is the saying pick n rectangles and find the area of those n rectangles. Then the limit says you get these approximations for different numbers of rectangles. If you use more and more of these rectangles, the approximation is better and better. It's leveling off towards some number. That number is what we're going to call the area. And what this problem is about is seeing what do those limits actually look like. So for a specific function x squared on a particular interval 1, 3, what is the limit of Riemann sums that we write down and say, if you were to compute this limit, the number you get would be the area we're looking for. And in this formula, there isn't a lot that we actually need to do. A lot of these pieces are, well, there's going to be a limit. That's just part of it. We know we're adding up some sums of these, adding up the areas of these rectangles. The function f is this x squared. So what the things that we actually need to find, given this template for what our answer is supposed to look like, is we need to think if we cut up our interval into n rectangles, what are their widths? That's what this delta x is, the width of our n equal size rectangles. And xi star, these are the test points that we use to figure out the heights. In this case, what we'll do, and what is really the default choice, is we'll choose these test points to be the right endpoints. And if we're looking for right endpoints, then what we actually need to do is if we draw our interval we're dealing with, what we have to do is say, take this interval, cut it up into some number of pieces. How wide are those pieces? And what are the right endpoints that you get? If you can find those, then that tells you what this expression is supposed to be. So the first part you can do is, what is the width? How wide are all of these rectangles? So the width is always going to be the formula b minus a over n. B minus a is the length of the interval that you're dealing with. Our interval is 1 to 3, but in general, AB is the interval you're looking for. So in our case, if we cut 1 to 3 into n equal pieces, then this is 3 minus 1, the length of our interval, divided by how many pieces we cut it into, which gives us 2 over n. So understandably, the width of the rectangles depends on how many rectangles you have. But this says, you give me the number of rectangles, this is their width. And in the problems that we had seen where we were given a specific number of rectangles, we wanted an approximation for that number, you would put that number in here. In this situation, what we're trying to do is say, come up with an expression that says that depends on how many rectangles you pick. And then we're going to say, take the limit of that and we get the actual area. The way that this gets used to try to find the right endpoints is that each of these intervals is delta x, which we found as a, or we can write, it is 2 over n, depending on the n. So how that's useful is we're saying, well, how do you find what these tick marks are? And the way to think about it is that each time you jump over, you add 2 over n. If you jump over to one more tick mark, You've gone over another rectangle width, so you've added another 2 over n. And you go over another one, you've added another 2 over n. So if we wanted to know what was, say, something out here, and I said, what if I take the ith right endpoint? I meaning which interval in our list of intervals are you looking at? And what this jumping little 2 over n is supposed to say is, well, how you find these points is each time you move over an interval, you add another 2 over n width, and you start it at 1. So x1 is we started at 1 and moved over 1 rectangle, which to start establishing a pattern is 1 plus 2 times 1 over n. The second endpoint, we moved over 2 of these, so we added this 2 over n twice. Which these have a common denominator, we can add the tops, is 1 plus 4 over n, or more suggestively written, is 1 plus 2 times 2 over n. With the point being, this 1 telling us which interval we're looking at shows up here in our formula. This 2 saying we're looking at the second interval shows up here in our formula. And in general, if we want what is the ith right endpoint, so you just pick some interval in the middle, you want to know what's the right endpoint. Well, you say, well, you're looking at whichever interval in our list. What you do is you have 1 plus 2 times I over n. Or written to look a little differently is you have 2 over n times I, which says you start at 1, you moved over I intervals, each interval added 2 over n, so that tells you where you ended up. And so this is the general formula. If you want to know what endpoint we have after cutting it up into n pieces, this is what those endpoints look like. And given the endpoints that we're using to test the height of our function and the widths of the intervals we're building rectangles over, we can start to come up with the area that we're looking for. So the area of the ith rectangle is the height times the base, but we know what these are. This is the general form, but the width, the delta x, is this 2 over n. This point right here, xi star, the ith right endpoint, it looks like this. And the f there is saying, well, we're looking at x squared, so that's what we want to do. Take this point and put it in our x squared function. So this is 1 plus 2i over n squared times 2 over n. Which seems like a bunch of symbols, but what this is saying is, given this situation, tell me how many rectangles you want to approximate with, and tell me which of the rectangles you want to look at. And this is saying, with n the number of rectangles, I the rectangle you're looking at, this is the area that it's going to be. So that's the area of one rectangle. The area of all the n rectangles is when each of them has this particular form, it changes depending on which rectangle you're looking at. But the area of all of them is the sum from the first rectangle to the nth, which is the last of our rectangles, adding up the areas of each one. So this is the sum from 1 to n of 1 plus 2i over n squared times 2 over n. And then the last part of this is saying, this is if you were to approximate with n rectangles using right endpoints, this is what you would get as your answer. The actual area is the limit of this. So the limit as n goes to infinity, so as you use more and more rectangles, of the sum from 1 to n, 1 plus 2i over n squared times 2 over n. So this area that we're talking about, that we could draw a picture and see it, there's some area of the shape that we end up with. This expression is, if you were to compute it, the value of that area. But right here, we pretty immediately see that if you wanted to come up with what number this is just the absolute wrong way of doing it. Like, how would you try to do this? There are ways to compute this, but they're more complicated than we want to deal with, and there's a better way anyway. So while it's good to, for the purpose of this, is to say there is a definite area, you can come up with a number. This is kind of the theoretical justification, but how do you actually find that number? So what we want to do is we really want to turn around and say, there is an area out there, but we need a better way of thinking. And to work our way up to that better way, we're going to introduce some new notation to help us talk about this. Because one thing which I think is especially perplexing about this is if I wrote this down, the fact that this is the area of x squared over some interval is not really clear. Maybe if we did some more problems like this, you can get practice at identifying what area this is talking about. But the fact that this is over the interval 1 to 3 is really not obvious. So while this works as whatever that is the area, as a notation, it's not the best. So here's how we'll start talking about this in a more streamlined way. So what we know so far is that if we have some function f greater than or equal to 0, then this limit, the limit as n goes to infinity, the sum from 1 to n, f of x I star delta x. Gives the area under the function over AB. But what we'll see once we build up some more machinery is this quantity that we're talking about, this kind of limit, still is meaningful even if your function is negative some places. Which means, well, if your function is negative, the idea of area is a little less clear what is being talked about, but this limit is still going to be meaningful. So we're going to say the fact that its area is not the emphasis, this limit is the quantity we're interested in. So here's what we'll say, a definition. For some function f of x on an interval AB, this limit, meaning, I'm going to sneak my way through here, this kind of limit that I don't want to write a bunch, so I'm going to not do that. So this limit is called the definite integral of the function f over the interval AB. And is written with this notation, which makes it clearer what function we're talking about and which interval we're looking at. So this is written with a big curvy S sign with an A on the bottom and B on the top coming from the interval, and then f of x dx. So this integral, or this definite integral, both the name and the notation look really similar to something that we've seen. So we had talked about before the indefinite integral, which was the integral of f of x without those bounds a, b. So this is supposed to be some number with the bounds, without the bounds. This is the antiderivative with the plus c, saying it's the general one. There is a reason why these are very similar that we'll get to. They are, in fact, very connected. A little more terminology to talk about this definite integral. The curvy S here is called the integral sign. The function f of x, the thing being integrated in this definite integral, this is called the integram. I won't really use this word very much, but if you're reading some, like the textbook or any other resources, this might come up, and that's what they're talking about, the thing being integrated. The numbers a and b in this notation are the lower and correspondingly upper limits of integration. And the last thing is that we will say that a function f is integrable. So able to be integrated, like differentiable, able to be differentiated. If the limit, again, just this limit exists and gives the same value for all choices of x I star. So for every way of choosing these test points, left endpoints, right endpoints, midpoints, something in the middle, if no matter how you choose those test points, this limit always exists and always gives you the same number, then we'll say this function is integrable. And the integrable ones are the functions that have an area. And while we won't really encounter them, what you can maybe appreciate is sometimes limits don't exist. And if you write this down for some function, it might be that this limit doesn't turn out to exist. And in that case, you can have a function where the area under it just doesn't make sense as a concept. A justification for why most of the functions we're going to look at are integrable is the following theorem. If you have some function f of x on an interval AB, only has finitely many jump or removable discontinuities, then the function f is integrable on the interval AB. So jumps, you're going in one place to some point, then you jump up to another point. Removable, this is when you have a hole in your function. And the idea is that if you have a function with finitely many of these, if your function looks like this and you have a hole here, so your function isn't defined at whatever this point is, that line here where your function isn't defined, that doesn't have any area, so it doesn't mess anything up. And also, if your function had a jump like that, you could say, well, let's look at the two sides of it. This area makes sense, this area makes sense. The fact that there's a jump, there's just one kind of line worth of uncertainty there, and that doesn't affect the area. Noticeably absent from this is, what if we said look at 1 over x on the interval 0 to 1. In this case, there's that vertical asymptote, and that's one way that you'd say, does area make sense there? Because we have this asymptote, it looks like there's an infinite amount of stuff because the space below this function is all of this. And there's a situation where area maybe doesn't make sense. So this is great. This is saying most functions we encounter, as long as they don't have asymptotes, really, I guess actually every function we encounter that doesn't have an asymptote, we can talk about the definite integral and its area. But how do we actually go ahead and find it? So one way that we can exploit what we know to help us find these definite integrals is that in some situations, we do know how to find areas. Although there's a twist that we have to deal with. So we had said if f is greater than or equal to 0, the integral from a to b of f of x gives the area under the function over the interval ab if f is less than 0 sometimes, then it can't just be area because area is always positive. Then in this case, the integral a to, or the integral a to b of our function gives what's called signed area. With the idea of signed area being that where your function is negative, your graph, there's some area enclosed there, but for the purposes of finding this definite integral, we're going to treat that as negative area, which starts to cancel out any positive area. So if we had, say, this, some graph that looks something like this. This is our function from a to b. Then what is the integral from a to b of this function? So we don't have a formula, we don't exactly know, but the way that we could interpret this is that we would say there's some positive area up here. There's this part of the graph which is above the x-axis. There's some area enclosed there. But then there's also this part of the graph below the x-axis, and that encloses some area there. So what this definite integral is going to be is this is find what that positive area is, and then subtract whatever this area is below the x-axis. And so the number you get, if there's more positive area than negative area, if there's more of the graph above the x-axis than below it, you're going to get some positive number. Yes.
But it's all that would you have to like make the or find the area for A, whatever the x-intercept is, and the x-intercept would be separately, or can you just all do it every time?
So if these were kind of what we'll see is if you could find them separately, this is a way you could do it. What we would really like is a way where we don't have to worry about where it splits in the middle. But you're right. If these were nicer shapes, we could really split it up and say, let me handle this part and then subtract. Yeah, so we'll see some examples where that's exactly what we're going to do. So there's a few examples of thinking of the integral as signed area. We can write down some integrals and actually evaluate them. So if I wrote down this expression, the integral from -1 to 1 of the square root of 1 minus x squared dx. Like, okay, that's some kind of symbols. And at this point, the way that we will need to evaluate this is we can say, this is some graph. What does the graph look like? And in this case, it turns out that this is a really nice graph, which lends itself very well to computing areas. This is the top, so it's a semicircle above the x-axis with a radius 1. So what this integral wants is, here's this function. This function is always positive. So in this case, this definite integral is just what is the area. And if I had said, what's the area of a semicircle with radius 1, you'd say, well, I don't need to worry about definite integral stuff. There's a formula for areas of circles, and I'll just cut that in half because I only have the top half. So this is 1/2, because we're just doing a semicircle, times pi r squared. The radius is 1, so that 1 squared doesn't do anything. So we get pi over 2. So if your graph turns out to lend itself or have a nice geometric shape, then we can say we don't need any calculus. This is just some notation telling us I want to find this area, and we can use the area formulas that we already know. There are some other cases where we don't have an area formula, but the point of view of sine area is still helpful. So what if we wanted to next find the integral from 0 to 2 pi of sine x? So sine is this wave, 0 to 2 pi is one of its periods. So if we draw this picture, and we're going from 1 to -1 out to 2 pi, pi's in the middle. We start at 0 and we go up, and then down at pi, and then we go down and back up by the time we get to 2 pi. And looking at this, one thing we don't know at this point is we have this first hump here. How much area is that? That's not a nice geometric shape that we know. So that's not something that we can really use. But thinking back to this picture, well, what we can say is that this area up here is positive area. This area down here is counting as negative area. And what we do know about sine is that it's very symmetrical. Each of these humps is exactly the same shape. This one has just been shifted and flipped upside down, but if you put them back on top of each other, they're exactly the same shape. So in this case, little waves have the same shape and size, but one of them is giving negative area. So what that means is we take whatever area this is, subtract whatever area this is, and we don't know what those numbers are, but it's the same number both times. So this is in fact 0. Because we know there's exactly as much positive area as there is negative area, and if we subtract those, we get 0, even without knowing what that area that both of these humps have is. Questions about this example, which we really aren't doing any work for, but what we're exploiting is we know that sine is very symmetric, and we can use that symmetry to our advantage here. Let me do one more of these, which uses. So another example of this signed area point of view helping us out. So let's see this. For this function f of x I'll define, which is going to be 2 if we're negative and 1 minus x if we're greater than or equal to 0. Let's evaluate the definite integral from -3 to 3 of our function f of x. So keeping in the pattern so far, that means draw this picture and figure out what areas we need to compute. So this is a piecewise function. To the left of 0, it's up at 2. So to the left of 0, we have a horizontal line at height 2. We're not using that at 0, so we have an open circle, but then we keep going that way, but we're stopping at -3. That's our lower limit of integration, and that's where we'll stop looking at the area. 1 minus x is a line that starts at 1 and goes down with slope 1. So it starts right here and goes down like this, but our upper limit of integration is 3, so we're stopping the area right there. So looking at this, we're using kind of a little bit of both of these. First of all, there are some nice, clean geometric shapes that we know the areas of. We have this rectangle here, and we have these two triangles. And we can look at each of them separately and say, what do we need to compute here? Well, there's this rectangle right here that gives us some area. There's this upper triangle, say call that T1. But then, well, these two are above, that's where the function is above the x-axis and get positive area. We have this lower triangle that we will also need to find the area of, but that's below the x-axis, so that's going to count as negative area.
Why would you want to find something that's left of the line going down?
What was that?
Why would you find something that's left of the line too? Yeah, like that triangle.
So which,
Like right below T1.
so what
Yeah,
this
like,
part?
yeah.
So what we're doing is when we're saying area beneath the curve, the way that we're interpreting that is they're going from the graph to the x-axis. So since the graph is up here, we're going down to just that x-axis, and then we flip below, we're going from the graph up to the x-axis.
Okay.
So it's always the x-axis is our kind of central line as we're going from the graph. So then if we want to find this definite integral, we can say there are 3 shapes we need to find the area of. What's the area of the rectangle? Add on the area of the first triangle, but then subtract off the area of the second triangle. And if that's what we need to do, then rectangles are base times height, triangles are 1/2 base times height. So figure out what those are. Rectangle base is going out to -3, so this length is 3. And our height is up at 2. First triangle, the base and height are both 1. So that's 1/2 1 times 1. And then our second triangle, the base and height are both 2 this time. So we get 1/2. 1/2 base times height is 1/2 2 times 2. And actually calculating these numbers, we get 2 times 3 is 6. This is plus 1/2. The last one, the 2's canceled to be -2. And so this is 4.5. Or 9/2 if you find a fraction.
If we're given a question like that on a test, are we gonna be given the graph or are we gonna have to make the graph ourselves?
So in this case, you would need to draw the graph yourself. And for problems like this, we're going to get another way of finding these definite integrals. Problems like this would say, compute the definite integral by, I guess, treating it as signed area. And in these cases, we've essentially seen what the things that can happen. They're either shapes where the area formulas are pretty easy, circles, rectangles, triangles. If that's not the case, then the other option is something like this, where there's some symmetry to be exploited. In this case, while so the sort of meta analysis of this problem is if you were given this and told to do it as signed area, you'd say, well, I definitely don't know the shape of this, but I must be doing something using signed area. So the only tool left is there's some sort of symmetry. And if you're thinking, how do I use that? There's some symmetry in here. Then the graph of sine could say, oh yeah, these are the same shape, even if I'm not perfect in my drawing. And so I have the same positive and negative area that must cancel each other out. So besides just being able to compute some of these areas as shapes, we also want to think about how can we take an integration problem and break it into sort of simpler problems. So what are some properties of how this integral works? The first two will look pretty familiar given what has shown up in a few cases. And this is if we have the integral from a to b of a constant times a function, then what you can do is find the integral of that function and then multiply by that constant afterwards. Basically, the integral is a limit, and you can always factor constants outside of limits. The thing like this always gets paired with something, another type of property, which says the integral from a to b of some function plus or minus another function is the integral of the first function, and then add or subtract the integral of the second function. So again, y is that when you have limits and things added together, you can break them up over addition and subtraction. You can also think of this function f plus g as saying you have the graph of f, and you added on the graph of g on top of it. And so if you want to find the area of them stacked on top of each other, find the area of each one separately and add those areas back. What we don't get to say is that if you have functions multiplied together, then you can multiply the integrals together. Like that didn't work with taking the derivative, that also doesn't work here. And also, for a point C in the interval AB, the integral from A to B of your function is the same as taking this point C, which is somewhere in the middle, integrating from A up to C, and then adding on the integral from C up to B. So this property is actually something that we used twice in this situation. The way that we looked at this was we said, we have this function, we have this interval that we're integrating over, break it up into 3 smaller intervals, find the integral over each of those separately, and then put those integrals back together to get the total. And as the very last thing, which are sort of weird to write down, but are kind of artifacts of the integrals, how it's defined is if you're integrating from A to A, so you have the same starting and ending point, the definition works out, so this is always 0. Intuitively, if you don't have an interval, you definitely don't have any area or signed area. And also, if it looks like your bounds are backwards, so typically we're doing this on the interval AB, you can write down this symbol, but if the bigger number is on the bottom, what works out when you check the limit definition of this is it's like you're finding the area, but everything is reversed. And that reversal gives you an extra minus. So this is minus the integral from A to B f of x dx. So you can write this integral down, but if the bigger bound is on the bottom, then you can write the bounds in the correct order by introducing an extra minus. So the takeaway from all of this is that we can find the integral by thinking of it as area. We also have some ways of handling integrals, breaking them into smaller pieces. What's unfortunate is none of this actually helps us find something like the integral of x squared from 0 to 1. And so that's what we'll do, I guess, in the video lecture that's going to be posted for you to watch either Friday or Monday. How do we actually find the integrals? And it turns out that the connection is the antiderivative stuff, the indefinite integrals, which has really similar notation. That turns out to be crucial, or the key point in how we actually find these areas, which is surprising. Okay, so that's where we'll stop. Friday is part of the people are taking the exam here, the rest of you are taking it on Monday. And good luck with your studying, and I'll see you at the exam. Right, so the problem would, the last thing would be approximate the area using a 4 rectangle. So those will be, but the one that says write down the limit or the area of the limit, that.
So the easy ones will be on that.
Yeah, the easy ones will be on